Hey everybody, we're going to start section 7.3 in this video, which continues on with confidence intervals, and this one is about estimating a population proportion using confidence intervals. And then we're also going to get into calculating sample sizes, minimum sample sizes necessary if we want to get a specific degree of confidence with our confidence interval, and also a specified margin of error. So first, let's talk about some terminology and notation. P is going to represent the population proportion. The way to think of that is kind of like as a percent. So generally, it's like if we want to find the percent of a population that has some characteristic, then that's what we're talking about when we talk about population proportion. And generally, we express this as a decimal, so the decimal form of the percent. So your population proportion will always be less than 1. And also greater than 0. P hat is how this baby right here is read, and that's going to be your sample proportion, which I'm sure you guys can guess would be the best estimator for the population proportion. Here's some little terminology right here, or notation I should say. P hat equals x over n. That's just how you find a proportion, right? You take how many successes you have and divide by the total number of things you are analyzing. Some other notation is this thing right here called Q hat, and Q hat is just the complement of P hat. So it's 1 minus P hat. That's really all you need to know here, is that Q hat will always equal 1 minus P hat. So that's something definitely to take note of. Confidence level, we've talked about these already. 90, 95, and 99 are pretty common confidence levels. Alpha is 1 minus your confidence level in decimal form, and z sub alpha over 2 is the critical value that corresponds with alpha over 2. So our confidence interval is going to look very much like, have the same type of form that our other one had. So when we were trying to estimate mu, we said it was between x bar minus some error and x bar plus some error. Well, we're not working with means anymore, we're working with proportions, so we're trying to estimate P. And we're going to say P hat is between, well, what's the best estimator for P? That's P hat. So it's going to be P hat minus some error and P hat plus some error. So you can see the form is very similar to the form of our other one. And P hat is pretty easy to find. Sometimes it'll be given to you, or you can just easily calculate it by just a simple division problem. And E is now the thing that we have to calculate, and E is given by this formula right here. So that's going to be your z sub alpha over 2, which corresponds to some confidence level, times the square root of P hat times Q hat over n. Okay? Cool. All right. So here are some requirements. You can read these over on your own. And these are just requirements for this method to be valid and give you actually statistically accurate probabilities and accurate intervals. All right. So the procedure, once you have your confidence level, your P hat, which you can calculate or maybe be given. Q hat is pretty easy to find once you have P hat. It's just 1 minus P hat. And N is, you're going to know. You determine your z sub alpha over 2. And then you calculate your margin of error. And then you use that and plug it into your confidence interval. And then you're done. And then just like on the last ones, we'd say I am, whatever percent confident that the population proportion of all such and such is between that lower bound and upper bound. So the author gives a round-off rule here. I think that's a fine round-off rule. They say 3 significant digits at the very end. That's a fine round-off rule. I probably won't strictly stick to that round-off rule myself. If your answer is given to you as percentages, whole number percentages, I might give the answer, I might go to that like one more decimal place than I was given rule. But they're both perfectly fine rules. So let's do an example together. So this one is going to be about recalling phone numbers. So a local company conducts a survey where people watch an advertisement which contains a phone number. Afterwards, they are asked to pick the phone number from a short list of numbers. In a simple random sample of 1,512 respondents, 474 picked the right answer and 1,038 did not. Okay, and we're trying to find the 90% confidence interval for the proportion of people who could correctly choose the given phone number. Okay, so what is our best estimate? Well, that's going to be p hat, which is simply going to be 474 out of 1512. So you'll see that calculation done right here, and we get approximately 0.313. Q hat is just the complement of p hat, so that's going to be 1 minus 0.313, which is 0.687. And our sample size is 1,512. All right. Next, the critical value, our z sub alpha over 2. So our confidence level is 90%. So we should know that the z sub alpha over 2 that corresponds with that is 1.645. And then we just plug these babies into our error formula. Here's our error formula. So the error is going to be 1.645 times the square root of p hat times q hat over n. And you just plug those things in, punch it all into your calculators, and it'll spit this thing out. So this right here is your E, your margin of error. And then for the confidence interval, we're just going to say P is between P hat minus some error and P hat plus your error. So we know P hat is 0.313. So 0.313 minus 0.0196 gives us this. So that's our lower bound for our confidence interval. And then we take p hat of 0.313 and we add on our margin of error, and that gives us this number, which will then be your upper bound for your confidence interval. So you have a confidence interval of 0.29. P is between 0.293 and 0.333. And the concluding statement we can say is that I'm 90% confident that the true proportion of all people who could correctly pick the phone number is between 0.293 and 0.333. Okay? Alright, cool. So, why don't you guys try this example on your own? Pause the video, give it a try, and then once you've finished, press play, and I'll go through how I would solve it, and we'll see if our answers match up. Okay, so we're going to try to find the 95% confidence interval for the proportion of all people who could correctly choose the given phone number. So a lot of the same data here is going to be carried down. Our critical value is really the only thing that's going to change. So we're working with 95% confidence now. So our z sub alpha over 2 for 95% confidence is going to be 1.96. Okay? So our margin of error is still going to be that formula we were working with before, which is z sub alpha over 2 times the square root of p hat q hat over n. So we plug our things in, which is 1.96 times the square root of 0.313. That doesn't look like a 3, but deal with it. 313 times 0.687. Get this box out of here. Oops, what is going on here? I don't know how to get rid of this box. Okay, I got rid of the box. And so it's 0.313 times our q hat of 0.687, all divided by our n, which was 1,512. And then we calculate that up and see what we get. And I got something like 0.023 0.02337. Cool. All right, so now we can plug this error into our general form of a confidence level, or a confidence interval, I'm sorry, and we get that, well, we know P is going to be between P hat plus the error and P hat minus the error. And so we can say that P is going to be between what's our P hat? 0.313 minus 0.02337. And I've got 0.28963. So I'm going to round that to 3 decimal places, and I'll say 0.290. And my upper bound is going to be 0.313 plus 0.02337. And I got 0.33637, so I'm going to write that as 0.336. And there you have it. That's my final answer. My conclusion would be that I'm 95% confident that the true population proportion is between 0.290 and 0.336. Or you could say I'm 95% confident, a little more casually. I'm 95% confident that the true percent of people is somewhere between 29% and 33.6%. Okay, cool. All right, I'll let you think about C and D on your own if you'd like, and we'll do some of that thinking in class. So let's move into part 2, which is calculating sample size. So this is exactly how we did it, or not exactly, but it's very similar to how we did last class, where we found this for the mean, and we took our error formula, and then we solved it for n. So you can do the same thing here. We have a new error formula here when we're dealing with proportions. And if you solve this baby for n, you're going to get this thing right here. All right, so that's mainly our formula for getting n, our sample size. If we have some desired level of confidence, which is what if that's the case, then we'll have a z sub alpha over 2, and some desired margin of error, that's going to be our e. Okay, and p hat and q hat, if you know this, then you can plug them in. But you're generally not going to know it, your p hat and q hat, because think about it. In order to know p hat and q hat, you would have already had to done the sample, which means you're not going to try to find your sample size. You've already done it, so you would have already had n. So this is maybe less practical, kind of like the mean stuff that we did last class, assuming that sigma was known. So more likely in reality, you're going to use this formula right here, which basically what they do is if you don't know p hat and q hat, then what's your best guess? Well, 50-50, I guess. So that's basically what this formula is. It plugs 0.5 in for P and 0.5 in for Q, and then 0.5 times 0.5 gives you 0.25. So if you have some kind of idea, I mean, p hat doesn't literally have to be known in order to use this one. You just want to plug in your best guess. So if you actually have some kind of a guess, maybe based on a previous study or something, then you would plug that in for p hat and get your q hat from that. But if you have no idea, absolutely no idea, then you're just going to use 0.5 here and 0.5 here, which would give you this 0.25. All right, so another thing to note about these n values when you're solving for these desired sample sizes is a round off rule. We're going to use the same one that we used last class, which is that you always round up to the next whole number. Okay? And we talked about why last class, and it's the same reason. So let's go through an example here together. Consider the example from the previous page about the phone numbers. The company wants to conduct another survey, but first wants an estimate of the required sample size given a specified margin of error. So what is the minimum sample size required if the company wants to be 95% confident that the sample proportion is within 2 percentage points of the population proportion? And assume that p hat is 0.313 as determined in the first study. So now we have some kind of estimate here that we can work with. So we're going to use this formula right up here. And we have p hat, so we're going to plug in z sub alpha over 2, which in this example, since we were looking for 95% confidence, is going to be 1.96. And we're going to square that z sub alpha over 2. Then we're going to multiply it by p hat and q hat, which is 0.313 and 0.687. And then you're going to divide by e squared. So for proportions, we're going to have our e be the decimal form. So if you're kind of considering, if your data is given to you like it is here as percentage points, we're going to turn that into a decimal, okay? Because our e and our p are decimals. Oh, well, we're going to turn e into it because our p is a decimal, okay? So you plug this in, plug everything in, compute it, and you get this number right here, 2065.2. So of course we're going to round up to the next whole number, which will give us 2066. All right, so why don't you try this your turn right here, and pause the video, give it a try, and then when you replay it, I'll show you my answer and we can see if they match up. All right, so we want to find the minimum sample size, so we're looking for n here, required if the company wants to be 99% confident that the sample proportion is within 1 percentage point of the population proportion. Assume no estimate of p hat is made. Okay, so we're going to use that formula for n, the z sub alpha over 2 squared times p hat times q hat all over e squared. Okay. And for p hat and q hat, we're going to use 0.5 and 0.5 because we have no estimate of p hat that we want to work with here. So our z sub alpha over 2 in this case, since we're working with 99% confidence, is going to be 2.575. So we're going to square that. Then we'll times it by 0.5 and 0.5, which you probably recall from earlier is 0.25. And then we'll divide all that by our e squared. And our e is 1 percentage point. So since it's 1 percentage point, we're going to write that as 0.01 and square it. And then when you plug all that into your calculator, you should get an answer of 16,500, oh boy, 576.56. Okay, so we're going to round this up to 16,577. All right, and that would be the final answer. And you probably are thinking, wow, that is a really large number. It's kind of a ridiculous sample size going after 16,577 people. Yeah, it is a large number, but you think about why it's a large number. You want to be 99% confident. That's a really high level of confidence. And you want the margin of error to only be 1 percentage point. That is a really narrow range that you're willing to tolerate here. So that's why in order to get a high level of confidence and a really narrow range, well, then you're going to need a really large sample size to get that level of accuracy. Okay, and you'll see a notice here made below, which basically kind of reiterates those same points I just made. All right, cool. Well, that'll do it for this video. I will see you guys in class.